So, welcome everyone. So, this is the problem solving session of Fundamentals of Power Electronics. This is week one, and I am Chandrima Chatterjee. I am pursuing PhD in Indian Institute of Technology, Delhi. So, what I will do is first I will summarize the first week lecture a bit so that that is also that is advantageous for you guys. And after that, I shall start the problems, right? Is it okay for everyone? Okay, so let's start. So in between, if you can't hear me or there is any question or any doubt regarding the topic I am now starting, so please just ask me, okay? Or if the presentation is not visible, then also you just interrupt me and just tell that it is not visible. Fine? Okay, so let's start. So I hope everybody has gone through the lecture, the week lecture of first week. So what we studied was the first of all the characteristics of the ideal switch, and then after that we started diode, which is basically the most basic semiconductor device, and afterwards then we studied the static and dynamic characteristic of diode, and then the power loss in a diode during the conduction loss, and also the losses during turn on to turn off transition and turn off to turn on transition. We also studied the thermal aspect, like if there is some power loss in the device, so definitely there will be some temperature rise in the device. So how to cope up with that, and how we can measure the different R thermal, like the R of at different junctions. And lastly, I think we also studied the different parameters that we see in the data sheet of a device, right? So I hope everybody have gone through the lecture. Is it like, have you gone through the lecture, or like some of you haven't gone through it? Please let me know.
Uh, I have gone to like I have not
Haven't
read
gone through it yet.
yeah, same
Okay,
here.
so I will suggest that before coming to the problem solving session, you please go through it once. Otherwise, because I only have limited amount of time, I will not be able to cover all the syllabus, like all the lectures here. So kindly please, like from next week onwards, kindly just go through it once and like listen to it. And then if you just attend this session, then it will be more effective, I feel. So yeah. So I will try to just cover all the topics that were taught in the first lecture. And if you have any doubt, so please just ask me. And I will also want this to be an interactive session. It's not that I will just talk all the like throughout the session and you will just be silent. Okay, so it will be advantageous if you ask me questions, or if you can share anything that you know, or yeah, like that. Okay, so I will start then. Sorry, I think my screen froze. Can you still see my screen? Yeah, okay, fine. Yeah. So, first of all, when we start studying power electronics, so for power electronics, we know that semiconductor devices are very important part of it. Why? Because with the semiconductor switches, we just make different kind of converters, which are usually very efficient, and we can design it in a way so that they are very compact, and yeah, obviously they are very efficient. And so we need to like study the characteristics of these semiconductor devices, right? Now, as we know that all obviously these semiconductor devices are not ideal. Obviously, they have many stray, like they have stray capacitances, stray different type of non-idealities. But first, to understand their practical devices, first we need to study the ideal devices. Then only we can proceed to practical devices and their characteristics. So if we just see one ideal switch, so for any switch, there are two states, right? That we all know. There is a on state and there is a off state. Now, for on, which we call as the on state of a switch, when the device conducts, right? When there is some current going through the device and it conducts, right? And the off state is uh, when it is turned off and it blocks some amount of voltage. So even if like there is a source, it will block the voltage and it will not allow the current to flow through the circuit. That is off state. For ideal switch, people are still joining. Yeah. So for ideal switch, if we see the during the on state, the voltage drop across that switch is zero. Like if we just turn on the switch, some current will flow through that switch, but the voltage drop across that switch will be zero, and it can carry infinite current. Like it can carry any amount of current when it is in on state. And also, if we see the off state, then obviously it can block voltage, any amount of voltage it can block. And the current will be absolutely zero. There will be no leakage current, nothing. The current will be zero, and it can block voltage in either direction, positive voltage as well as negative voltage. Like in forward direction and reverse direction, it can block voltage. Is it clear?
Okay, ma'am.
If you don't have like you if you don't understand any point, if it is not clear, you can tell me. Okay, no problem. I can repeat it. And lastly, like in for ideal switch, the time it takes to turn on and turn off, it is zero. Like it can instantaneously turn on and instantaneously it can turn off. It doesn't take any time to for the transition to go from on state to off state and vice versa, right? So these are the properties of a ideal switch. And actually, if you see, like I have not drawn the devices, but switches can be controlled as well as uncontrolled. Okay. So for uncontrolled switches, you can't decide when the switch will go from turn on to turn off or turn off to turn on. So the circuit conditions will dictate whether the device will be turned on or it will get turned off, right? You can't decide it. But for controlled switches, you can decide when you want it to be on and when you want it to be off. So there is a signal, we call it as the control signal. So for these switches, there will be three terminals. Two will be power terminals and the third terminal will be a control terminal through which you can give some control pulses. So based on those pulses, it will the switch will be turned on or switch will be turned off. Right. So those are called controlled switches. We will study during this like during the this course, we will study both kinds of switches, controlled as well as uncontrolled, right? So let's proceed to the next one. Yeah. So if you see this circuit, this is a simple circuit, right? There is a voltage source and there are two resistors, right? You can see it here. So suppose somebody asks you that this okay, I will just use the mark pointer. So across this resistor, I want a I want a 50 volt, right? So that is very pretty straightforward, right? Because there are two 10 ohm devices and there is a 100-volt source. So can you tell me what will be the current through this circuit? What will be the current? This is pretty straightforward, right? Hello?
It's
One
10
amps, ma'am.
amps.
Sorry?
It's 10 amps.
How are you calculating it?
So if you don't see the circuit as a voltage divider, then it is like a resistor, series resistor circuit, and you are
Right?
passing a 100 volt. And in the series circuit, the current remains same. Voltage is actually divided into different resistor, but the current remains same in the series circuit. And you have a 100 volt, and you have a resistor of 10. So the normal Ohm's law is I is equal to V by R. So 100 is a volt divided by 10, so which is 10 amps.
Yeah, like about the Ohm's law, you were right. But is the what is the equivalent resistance of this circuit? You don't think about voltage
20.
divider and all. 20, right? So according to
Five.
Ohm's law, it should be 5, right? 100 divided by 20, not 10 ampere.
Yes, ma'am. 5 amps, ma'am.
Yeah, it should be 5 ampere because the equivalent resistance, these two resistors are in series, right? 10 ohm and another 10 ohm. So the
Yeah,
equivalent
correct.
resistance is 20 ohm, and so your current becomes 100, 20 upon 100, right? Sorry, 100 upon 20. So it is 5 ampere. So like so then if 5 ampere is flowing through this circuit, then across this 10 ohm and across this 10 ohm, the voltage drop should be same, right? Because they are equal resistances. So the voltage across this resistance will be 10 multiplied by 5, right? Because the current is 5 and the resistance is 10, so the voltage drop is 50. And again, across this resistance, the voltage drop is 50. So this way, by putting like proper value of the resistor and using it as a resistive divider, you can have a voltage like you can step down the voltage like from 100 volt. If you tap the voltage here and here, you can get 50 volt. Am I clear?
Yes, ma'am.
Yeah. So like that, you can get a voltage which is lesser than the source voltage. This is one way. But there are some shortcomings for like there are some shortcomings. What are they? Can anyone say what could be the shortcomings of stepping down voltage in this way?
Power loss across resistor.
Yeah, right. You were right. So the problem is that even though you are getting a lower amount of voltage, but the problem is half the voltage is getting dropped across this resistor, and this drop is of no use to you. So the power is getting like dissipated across this 10 ohm, which is getting lost as heat. You can't do anything about it. So the effective power that you will get is like half of this source power, right? So this is completely lost, and then the efficiency becomes very bad. And we don't want that. We want very highly efficient circuit. So this is not a good way to get a to get a lower value of voltage by using resistive divider. So that's what I have written here. Think.
Efficiency means?
Actually, yeah. So efficiency means that efficiency, if I say like in a just a sentence, so efficiency means your output power divided by input power, right? So if we suppose this is your load, this 10 ohm is your load, you like whatever power you are getting across this resistor, that is your useful power that you will use somewhere. Although this is resistance, but just imagine is at as your load, and the power that you are getting at this point, this is your effective power. So if you see the 5 ampere current is flowing here, so what will be the power? The power will be your current I square R, right? So I square is 5 like 25 times 10. So that is 250, right? Is it clear how we are getting 250 watt here?
Yes.
Yeah. And from the source, how much power you are drawing? So the source voltage is 100 volt, and the current it is feeding to the load, it is 5 ampere. So from source you are getting 100 times 5, which is 500 watt, right? So your output power is 250 watt and your input power is 500 watt. So what is the efficiency now? If efficiency is equal to output power by input power, so what is your efficiency now?
It's 50%.
It's 50%, right?
Yeah.
So you can say like 50% efficiency is not good. Like if you talk of an electrical circuit, 50% efficiency is not at all a good efficiency like value. So yeah, so if you use this kind of resistive divider circuit, that is the problem. That some of amount of power you will have to sacrifice in the process to get a lower amount of voltage across your load or something, right?
Yes.
Sorry, my screen is freezing again and again. I don't know why.
Ma'am, maybe transcript tool uh, be the reason.
Sorry.
Maybe the transcript tool might be the reason.
Okay. I will just hide it then. No, now also it is not happening. Mm. So I will just stop sharing and then again share. Okay. See. Yeah, is it visible?
Yes, madam.
Okay, okay. PowerPoint is not. Okay. So I think now it is coming. Okay. Yeah, so whatever I discussed so far, that's what is written here, that only 50% power is supplied to the load and the solution is lossy. So this can't be a solution, right? So then what could be our solution?
Ma'am, screen is not visible.
Okay. I will just share it once more. Okay, now?
Yes, ma'am.
Okay. Now can everyone see the screen?
Yes,
Yes.
ma'am.
Okay, okay. Sorry for the interruption. Uh, so yeah. So what I was saying was that the previous solution we can't use, right? So another solution could be, that's where the semiconductor devices come into picture. So what we can do is we can put a uh, we can, one second, we can just put a semiconductor switch in series with this source, and afterwards we can have our load. So what will happen is, as we already discussed the properties of the ideal switch, what will happen is when we will turn on this switch, so the circuit will be complete, right? So then the the source voltage will provide current, like the current will flow through this circuit. And we will when we will be like, no, we don't want any current, so we can turn off this switch, and then no current will flow through this circuit without any extra loss, right?
Yes.
And yeah, so okay, just wait 1 minute. Just So how will we do it? We will do it in a way. Suppose this is suppose this is our waveform. So see, this voltage, the source voltage is 100 volt, right? This is a constant DC source. But what if we can like turn on and turn off this switch in a way so that, like, suppose for 50 if this periodicity is t, suppose this time period is t, for 50% of time we will turn on this switch. The duration will be 50%. So during this time the voltage across the load will be 100 volt, and after the 50%, the remaining 50% we will turn it off, so there will be no voltage across this load. So the voltage across the load, the wave shape will be something like this. So for 50% 100 volt, and rest of the 50% it is 0. Again this sequence is repeated, right? So did you understand what is happening here? So this basically, like, you will learn this afterwards, but we basically call this duty cycle. So the duration of time till which the one switch is on. So here for 50% time we are turning on this switch, and for the rest of the 50% the switch is off. So like this we are having a pattern. So the average voltage here we get is 50 volt. If you take the average of this, so for some amount it is 100 and for some amount it is 0, and this is 50-50. So if you take the average it comes out to be 50 volt. So without incurring any loss we are getting half of this voltage, right? Am I clear?
Yes, ma'am.
Yeah. So the here the advantage is very obvious, that we are not incurring any loss, unlike the previous one, right? Here the, as we are assuming an ideal switch, so no drop occurs across this switch and no power loss is there. So without incurring any loss we are just getting 50 volt across this load. Yeah. So after that we will go to the diode, right? Basically, so diode is, you can say, the simplest form of a semiconductor switch. We also call this a PN junction, right? We call it PN junction diode. So what is a PN junction diode? A PN junction diode is, here we, like, I will not go into the device physics or the doping mechanism and all, but simply we can say that there will be some, this is obviously some semiconductor, and then with that we do some doping, some p-type material and some n-type material, right? And with the doping we get a semiconductor which we call a PN junction diode. Why a PN junction diode? Because there is a junction of p-type material and n-type material, right? So the symbol of diode is something like this. So this is a symbol, and there is this like this, there is a line, and there are two terminals, as you can see. One terminal we call as a anode, and another one we call cathode, right? So so some of you must be knowing, like, already what a diode is, right? Some of you, do you know, some of you, like, what is a diode and how does this function?
Yes, madam.
Yes. Yes.
Yes, ma'am.
Yeah. So, diode is like, it is a very simple device, right? So first of all, we will see the characteristic of an ideal diode, and then we will see the characteristic of a practical diode, right? So for diode, it is an uncontrolled device. Why it is an uncontrolled device? Because I mentioned that for control device you will be seeing three terminals, not two terminals. So if it is a control device, you will see another terminal through which we will provide some control pulse, and based on the pulse, the device will be on and off, right? But for diode, there are only two terminals, one cathode and one anode. So we can't control when it will get turned on or when it will get turned off. So based on the circuit condition, so wherever you are using it, so then it will be on or it will be off. And another property of diode is it can block voltage only in the reverse direction, right? So what do we mean by reverse direction? So this anode terminal, so for the diode to get to turn on, you'd when first of all when we give, like when this the potential of this anode terminal is positive with respect to the cathode terminal, then only the diode will be on. So that's what I have written. This we called as a forward bias. So when VAK is greater than 0, then only the diode will be on, otherwise it will be off. So the potential of this point, this anode terminal, should be greater than the potential of this point for the diode to get turned on. Is it clear? What is the condition?
Yes.
Yeah. So, and if the case is opposite, so the potential of cathode terminal is greater with respect to the potential of anode terminal, then we call this a reverse bias. And in that case, the diode is turned off and it can't conduct, right? So diode is also a unit, like it can carry current only from anode to cathode, an ideal diode I am saying. It can't, so that's why if you see this characteristic, this IV characteristic, so here the current direction is in positive y-axis. The current we have not shown in negative y-axis because it can only carry current in this direction from anode towards cathode, not the opposite, like from cathode to anode it can't carry current. And when it is off, like when it is in reverse bias condition, it can block voltage. Like if the voltage is negative, so with respect to VAK, the voltage VAK, this we assume as the positive voltage. So it can't block voltage in this direction. If the moment VAK becomes greater than 0, it will start conducting, right? So it can't block voltage. But if VAK is less than 0, then it can block voltage, meaning that it will not conduct any current. It will, the whatever voltage you are applying, the voltage will appear across this diode and it will block voltage, like it will be off, it will not carry any current. Is it clear? How are we approaching, like
Yes.
how are we getting this characteristic?
By changing voltage, ma'am.
Sorry.
By changing voltage.
Yeah, right. Changing voltage means like first if we are talking about ideal diode, so whenever you will just apply a very small amount of voltage, like it is just above 0, then it will start conducting and it will conduct current like this, like without any drop across it. Just we have, sorry, if kindly please mute. Yeah. So it will start conducting current the moment VAK becomes greater than 0. And as we are talking about an ideal diode, so there will be no voltage drop across this. Like it will be, the locus will be the positive y-axis. That's it. No drop. And when VAK is less than 0, there will be no current and it will block the voltage. Whatever voltage you give, whatever negative voltage, it will block it. It will not allow any current. Right? So that is the property, like that is the this is called a static characteristic, and this is the characteristic of an ideal diode, right? Now we can now we will proceed to see what an actual practical diode characteristic is. This is ideal diode. Obviously we don't get this kind of characteristic in real life. There are some non-idealities associated with a diode. So this is the characteristic of a non-ideal diode, right? So if you see earlier here what we see, this is the ideal diode characteristic. So the locus is positive y-axis and negative x-axis, right? So the x-axis is voltage and y-axis is current. For practical diode, there is some amount of voltage which we called as the threshold voltage or the cut-in voltage or knee voltage. There are different terms. So unless we cross this voltage, the diode will not turn on. This is a very small amount of voltage, like it is usually typically zero 0.6 volt, or there are some other values. It may be 0.7 volt or 1 volt or something. But if the positive voltage, like the voltage VAK, doesn't cross this value, the diode will not turn on, right? So this is one non-ideality. Another non-ideality is here. For the ideal case, you could see that the current is like perfectly vertical. It is just following the positive y-axis. But here there is some slope, right? You can see, right? There is some slope. So if there is some slope, so there will certainly be some resistance, right? If there is a some slope between the voltage and current, like this characteristic, so there definitely will be some resistance associated with the diode, right? So that is in the forward bias condition, and in the reverse bias condition, you can see here the locus was negative x-axis, but here there is very small amount of current. What we call it as a leakage current, right? So very small current flows, but that is negligible almost. But very small amount of current flows in the reverse direction, and there is some break the at some point when you are giving negative voltage, the diode breaks down, meaning that the diode can no longer block the voltage, so it breaks down, and this we called as the peak inverse voltage, right? Beyond this voltage the diode can't withstand, so the diode will get damaged. And then, like, so that's why we shouldn't cross this voltage ever. If we cross this voltage, like negative voltage, then the diode will break down and it will get damaged. So am I clear till this point?
Ma'am, in
Just
the
one
negative
question.
voltage, the current have to be blocked.
Sorry, can you repeat once?
Ma'am, in the negative voltage, the current have to be blocked.
Yeah, the current needs to be blocked. For ideal diode, it blocks it precisely, like it doesn't allow any current. But as this is not an ideal diode, we are talking about a practical diode, what we usually get. So there is some non-ideality, right? So whatever current you are seeing in this region, so this current is very small. Like so this is a leakage current. This will be in some, like, this is very small. So we can neglect this value. Okay, so this doesn't harm the operation of the circuit, but yeah, there is some leakage current. It can't it can't block, like the it can't just block it ideally. In practical diode, you will have to, like, there will be some non-ideality, and this is one of the non-idealities. So it will allow some amount of leakage current, but this is so small that it doesn't affect any operation of the circuit. Like, it is okay. So if you ever, like, test a diode, you will see that, right? So, like, this current doesn't harm, like, doesn't that will not affect your operation of the circuit, right? Did you understand?
Right,
I
madam.
have one
Got it.
question.
Yeah.
In this graph, it looks like that leakage current will start flowing only when the voltage is less than some zero, when the direction immediately changes. Is it like that, or the leakage current is there, will be present when the voltage is below the threshold, or whether it will flow only when there is a reverse voltage.
Uh, yeah, actually, in the reverse direction, we can't really comment. Like the threshold voltage concept is only in the forward bias direction. So, like, even though it is shown like this, but the current is not like, it is kind of a like exaggerated version. So, current is not also this much. It will be like very small if you just search in the web, like or you can see any textbook where the diode characteristic is shown. This current is almost like it is just following this axis only. Like, it will be very, very small. So, we can't really
I
comment like,
understand that it's a
yeah,
I
yeah, yeah,
understand that it's a negligible current.
yeah.
The leakage current will be very small and it's a negligible current that I understood.
Uh,
My only
hmm.
question is whether that leakage current will start flowing only when there is a reverse polarity, or for the conduction we have to go, let's say if it is germany or silicon, like the threshold will vary from point 0.3 to point 0.7, right? So if
Right.
the voltage level is like something around 0.1 or 0.2, will there
Hmm.
be a leakage current for that voltage also? Or whether the current will come into picture only when there is a reverse polarity? That is my question. I know that the leakage current will be very small and it is like negligible only. That I understand. I just
So
wanted to
you
know.
were, if I understood correctly, you were asking if there is in the reverse direction also, it will the current will start flowing after some threshold, or whether it will start immediately after some reverse voltage is applied. Uh, am I
Yes, yeah, that's correct.
yeah. So uh, as far as I know, I don't think there is any threshold voltage concept in the reverse direction. So, but yeah, like I will also see. You guys can also check, but in the threshold voltage is only we define in the forward bias direction. In the reverse bias, I think there is nothing like some threshold will be crossed, then only the current will flow. Because yeah, and
Okay, thank you.
another thing is like another phenomena is called a reverse recovery phenomena that I will talk about after some slides. So there you will see that when the diode gets turned off, some amount of reverse current flows, right? And that current is like substantial, but the current flows for a very small amount of time. So I will explain that later, right? So that is called reverse recovery. So in that time also some amount of reverse current flows. So yeah, so we will proceed. Yeah, so what I was saying is that as you can see some slope here. If you see like this may appear to be a constant like this may appear to be a straight line, but it is not. Actually, if you see the diode characteristic, it goes something like this, right? So this resistance is called dynamic resistance. Why dynamic? Because the slope is not constant. This relation, like this VD and I, this relation, this is an exponential relation. So at each operating point, the resistance value will be different, like based on this equation. So this is called a dynamic resistance. But yeah, obviously for our ease of calculation and ease of understanding, what we usually do is we do an approximation. What approximation? So instead of this characteristic, we do a piecewise linear. We assume a piecewise linear model. What is the piecewise linear model? Uh, I will just try to show you. So actual characteristic is something like this, like some, sorry for the bad drawing. So it will be something like this, right? Some exponential relationship. But for our ease of standing, what we do is we will just, this will be, sorry. This will be as it is, this threshold voltage, and afterwards there will be a straight line. So this second one, we call it as piecewise linear model because we are linearizing this. Instead of this relationship, we will follow this one. So in this way, the resistance will be constant because this is a straight line. So the slope of this will be constant. So we will, but for this one, the slope is constantly changing, right? At this point, at this point, at this point, the slope value is different. So instead of that, we can take a constant resistance. That's why we will, like, afterwards we will follow this piecewise linear model of a diode. Is it clear?
Got it, madam.
Yeah. Okay. Okay. So let's proceed to the next one. So yeah, I was talking about the reverse recovery, right? So if you see, when we apply a reverse voltage across the diode, so suppose this is the initial condition when the diode was conducting, it was forward biased, right? So suppose there was some source and the diode was there and current was like it was carrying current, right? So this was the current. Just wait a minute. Just yeah. So suppose it was carrying some current, right? Now the voltage, we have applied reverse voltage. Okay. So what will happen then? So the current now like for ideal diode, what would have happened? The current will immediately become zero and there will be no current. Like in zero time, it will from this current, it will immediately become zero and it will remain zero. But for actual diode, it doesn't happen. What happens is the current, there will be some slope with which the current will come down. It will reach zero and it will go negative. It will not stop here. It will go negative and then after some time it will become zero. You can see this characteristic, right? So what happens here is basically, so in the junction, in the diode junction, in the PN junction, when it is carrying current, some charges are stored, right? So if the diode has to block some voltage, those charges will have to be recovered. Those charges needs to be removed from the junction, right? So that's why for removing these charges, there is a negative current that flows. And after this negative current, like all those charges are recovered, then only the diode starts blocking the voltage. So if you see the voltage across this diode, this is VAK. So there is some positive drop across this diode, right? When it is carrying current. And then till this point, there is still some positive drop. And after that, only after this point, when the current is becoming like it is slowly becoming zero, then only it starts blocking the voltage. And after the current is completely become zero, then only it reaches the whole reverse voltage and it starts blocking. So, so did you understand what is happening here?
Yes, madam, got an idea.
Yeah. So the main point is that whatever charge is stored in the junction, it needs to be removed for the diode to block the voltage. Unless it is removed, it can't block any voltage. So that's why the current becomes negative. So now the charge is getting removed. And then after the current becomes completely zero, then it can block this voltage. So that's what I have written here. This phenomena is called reverse recovery, right? And you can see that during this portion, this is the portion where the diode, the transition is happening from turn on condition, it is going to turn off condition. So there will definitely be some loss because there is some voltage and there is some current. And whenever voltage and current overlapping happens, some loss occurs, right? Some power loss will be there definitely. So during reverse recovery, some power loss occurs. And how can we calculate this power loss, that we will see later. Can you please mute yourself, whoever is on mic is on. Yeah. So is it clear for everyone? Okay, so we will proceed. Yeah. So now we can talk about the power loss, right? Like, what is the power loss? So actually for the ideal diode, there shouldn't be any power loss. But actually, like, it doesn't happen like that. There is some power loss that happens in the diode. And we will see what is the power, how can we calculate this power loss, right? And this is a very important point because based on this power loss, we will have to design the heat sink and everything, right? So I will talk about it. First of all, we will see what is the power loss. So if you see, like earlier, we talked about some threshold voltage. If we like beyond this threshold voltage, the diode starts conducting, right? If we are even if we are we are giving a forward voltage, that forward voltage will have to be greater than the threshold voltage for the diode to turn on, right? So this forward voltage we represent as a voltage source like this VF, and there is this dynamic resistance RD. So this is the equivalent model of a practical diode. There is this resistance, along with that there is a voltage source which is basically the threshold or the knee voltage, right? And current flows from here to here. So this is the diode symbol, and this diode we can represent like this. Understood? And if we see the voltage across the diode, so VAK would be VA plus IAK RD, right? Is it okay?
Yes, madam.
Okay, the others, is it okay? Like, did you everybody understand what I tried to say? Okay, so,
What is VF?
sorry,
Ma'am, what is VF?
VF is this voltage. So earlier we saw that there is some threshold voltage, right? So this voltage we call the threshold voltage. Like here it is 0.6 volt is written. So for some diode, it can be 0.7 volt or lesser than that or somewhat greater than that, right? So typically it is 0.6 volt if we just assume. So this voltage is called threshold voltage or cut-in voltage. So whenever a diode is forward biased, and if you are applying a forward voltage across this diode, so unless this voltage we exceed this voltage, the diode can't start conducting. Whenever this zero point 0.6 volt we exceed, then only the current starts rising, right? So if you want to represent it electrically, how will you represent it? This is a constant voltage, right? So we represent it in terms of a constant DC source. So this is what we call it the VF, right? You can call it, you can denote it as VT also, or VNE, or VNE point, like anyway. So this is that voltage. And this RD is the resistance of the diode, right? So if you are expressing it as the piecewise linear model, it will be a constant resistance. But just wait a minute. Hello? Yeah. So sorry for the interruption. Could you please mute? Yeah. So please mute yourselves. Unless you don't have a question, please mute. Otherwise, it will be difficult to continue the session. Yeah. So what I was covering is that the power loss during conduction period, right? When the diode is conducting some current. So somebody questioned that what is VF. So did you understand what I explained? What is VF?
Got it, ma'am. Hello.
Yeah. So VF is basically the threshold voltage, right? What we this voltage we need to cross in the forward direction so that the diode can start
Don't talk.
conducting. Yeah. Sorry, did you say anything? Did anybody ask anything? I couldn't hear properly.
Madam G. Viratham, mic is open.
Madam, when I close the mic, I can't able to hear the audio, madam.
Okay. Just what's your name?
Jeevaratinam.
Okay, just 1 minute.
If I close,
Yeah, so now can you hear? Just give me a thumbs up if you can hear it.
yes, madam, I'm receiving audio.
Okay, fine. Okay. Okay, so yeah. So now if we just calculate the power loss during conduction, so what will be the power loss? So the power we know like what is the general method of calculating power loss? It is we will just have to integrate. So for the energy, what is the energy? Energy loss is VAK times IAK. And for the power loss, we will have to we will have to integrate it from 0 till the time period. And again, we will have to divide it 1 by TS, right? So this is the generic formula for calculating any power loss, right? In an electrical circuit. Now, so we will have to average over one cycle, right? Now, as we see that this VAK, this voltage across the diode, this we have already written as this expression, VF plus IAK RD. So we have replaced this VAK as this expression, right? Is it okay till this point?
Yes, madam.
Yeah. Now, the next step would be this. So VF is a constant value. As I already said, this is a threshold voltage and this is a constant value. So we can take it out of this integration. So it comes out to be 1 by Ts, this integration of IAK dt. And then again, there is IAK squared dt over 1 by Ts, right? And this RD is also there. So what is this expression? Can anybody tell? What will be this one? What we can call it?
Average current.
Right. This is average current. And the next one, the second term.
RMS current.
Right. So eventually what we get is VF times this average current and then this IAK RMS square times RD, right? Because this expression is of a average current and this expression gives us the RMS current squared, right? So if we want to calculate the conduction loss, this is the way. So we need to know the average current that is flowing through the diode and we also need to know the RMS current. So then only we will get the whole expression, right? Is it clear for everybody? Okay. So we have so now we
Madam,
have yes.
madam, why it can't be I average square, madam? Why is IRMS square?
So do you know what is average current and what is RMS current and how we do it? So if you want to get the average of any quantity, not only current, like in general, if you try to find out the average of any quantity, so this is the way to do it. You need to if there is the periodicity is Ts, Ts means the time period after which the sequence gets repeated, right? So if you know that, so you will have to take so for finding out the average, you will have to compute this expression. So whatever quantity average you want to find out, so that will be within this integration. In this case, it is current. So if this is any other quantity, that will be there along with time. So over time, it will have to you will have to integrate it, and then you will have to divide it by the time period, right? So this is the way to find out average for any quantity mathematically. And this is the way to find out RMS of any quantity. So the concept of RMS current comes from the heat, right? So if a current is flowing through a circuit, there will be some heat, due to the energy loss, there will be some heat dissipation, right? It will the energy will get dissipated in the form of heat. So from that concept, this RMS current came, right? So the way to find out RMS of any quantity is this. If you can see any textbook or any so this is the out of my scope because I will not be able to complete the whole lecture. So we
Okay,
can
madam.
you just see once, okay? And you
Okay, madam.
see that whenever we try to calculate any RMS value, RMS quantity, so this is the way to get it, right?
Okay, madam. Thank
So
you.
yeah, if we have time, we can get back to it, right?
Okay, madam.
Yeah.
Madam, I'm not getting the screen.
You are not seeing the screen.
Yes, madam.
So others, can you see the screen? or you are
No,
also
madam.
oh, okay, okay, let me check. Sorry. So you should have told now that you can't see the screen. Okay. Okay, now?
Yes, madam, getting.
Yeah, okay, fine. So, yeah. So now you just see this is the expression, right? Okay. So till this point, are we okay, everybody? Okay. So next is yeah. So next we will talk about the reverse recovery loss. So earlier when I was talking about the reverse recovery, then I explained that as there is some negative current and there is some voltage also across the diode, so there is an overlap of voltage and current, and whenever there is an overlap of voltage and current, there will be some power loss, right? So during the conduction period, we already saw the power loss. So, as there is a threshold voltage constant drop and also there is a resistance associated with the diode, so there is some power loss during the conduction period. Here also, when the diode like starts, like when there is the transition is happening from turn on condition to turn off condition, so there is some overlap of voltage and current. So there will obviously be some power loss. So so we know that the reverse, if we just want to calculate the charge, the reverse recovery charge, right? So we denote it as QRR. So if you just imagine, like we can assume it as a triangle, right? Though this is not a triangle, but we can approximate it as a triangle. So if you want to just calculate the reverse recovery charge, that would be half IRR TRR, where IRR is this peak of this current. So the area charge is basically area under the current curve, right? So the current curve is this, and the peak value is IRR, right? So the height is IRR and the base is TRR. What we call is at the reverse recovery time. So the charge will be half IRR TRR, and the energy loss will be half QRR into VR, as we know the charge, and if we just multiply the charge and the reverse voltage, so that gives us the energy, right? And the power loss will be like energy into the operating frequency, or you can also write it as ERR by TS, right? So FS is basically reciprocal of TS. So this is the inner power loss during reverse recovery. Okay. Is it okay?
Okay, madam.
Okay. So next, the power loss during both the conduction loss and the reverse recovery loss, we will explain. So suppose we are giving this kind of a voltage to the diode. So first it was positive and then it becomes negative. So this is the voltage, like this is the source voltage waveform. Like x-axis is time and y-axis is the voltage, right? So this is the voltage, and it is like periodic in nature. First it is positive, then becomes negative, again the same pattern is repeated. So what will be the power loss in the diode, right? That we need to see. So this picture I have taken from the lecture only. If some of you have listen to the lecture, you will know that what was discussed there. So first, if we see, so during this portion, the voltage is positive, so the diode is forward biased, right? And this is the load resistor. Though, so the current value, the current flowing through the circuit will be approximately V1 by R, right? So this is the current. Now, again, when the voltage becomes negative, then the diode will stop conducting, right? So there will be some very small period, the reverse recovery period, when it will retrieve the charge, the charge will be removed from the junction. So this is the negative current that we like. So this is the zoomed version that I already showed you. This is the negative current. So here it is shown here. And then the current will become zero, right? And again, this pattern is repeated. And for the voltage across the diode, when it was conducting the current, there was very small amount of voltage drop VAK, as I already explained during the conduction loss calculation. And after the reverse recovery is done, it starts blocking this reverse voltage because here the voltage is negative. And again, when the voltage becomes positive, again it starts conducting. So the voltage becomes like, so again the voltage drop is like very small. And this pattern is repeated, right? And if we just see the power loss, so here there is some amount of power loss during conduction, and then there is some power loss during the reverse recovery, as I showed you in the earlier slide. So some power loss during this reverse recovery, then the power loss is zero. And again, during the conduction period, there is some power loss and this gets repeated. So one thing to note here that I talked about the transition from turn on to turn off, but I didn't talk about from turn off to turn on. So for diode, the time taken to from during turn on, the time taken is very negligible. Like I am talking about this transition. So the overlap between voltage and current is very small. So we don't usually talk about the turn on loss for a diode, but the reverse recovery loss is substantial, so that's why we talk about it, right? So yeah, so here it is written. You can always go to the lecture and see whatever is discussed there the power loss has been discussed elaborately. So if you want more insight on it, you can always visit the lecture. Just one moment, I will just see. So till this point, is it okay? Hello?
So, madam, it means that loss occurs in both the scenarios, on situation also and off situation also.
Right. So if you see any semiconductor device during both the transitions from turn on to turn off and vice versa, some loss occurs. But for diode, the for diode, this from turn off to turn on, this loss is very negligible. But from turn on to turn off, as the reverse recovery occurs, so that's why there is some loss, and this is like substantial. But during this region, the loss is very small, so usually we neglect it. Like this is not very this is not a very what should I say, very significant value. So we don't usually consider it, right? But some loss occurs, yeah. It is not zero completely. Yeah. So now we will talk about the thermal aspect. So as I already mentioned that as some power loss occurs in the diode, so and this loss is this comes out as the heat, right? So as heat is generated due to the power loss, so the junction temperature of the diode rises. More the power loss, more will be the junction temperature. And there is certain, for if you see in data sheet of a diode, so there is some allowable temperature beyond which it can't withstand. So if the temperature goes beyond that, the diode will be damaged. So we can't allow it to go beyond that temperature. So what we do is we use some heat sink. What is a heat sink? A heat sink is a heat sink is what helps to dissipate the heat from the device. So it will be its thermal conductivity should be very high, and it should just take away the heat from the device and it should dissipate it in the ambient, right? So that is the job of a heat sink. So whenever you will see a practical converter, wherever there is the devices are there, so you will always see some heat sink is they attached with the device so that it can dissipate the heat, right? And the device doesn't get heated up. So to calculate the temperature rise, so we need to get some equivalent circuit, right? And the equivalent circuit we will represent in terms of electrical parameters for our ease of calculation or our ease of understanding, because we are studying electrical engineering like electrical power electronics. So we will represent all the things in terms of electrical parameters. So as you already know that in an electrical circuit, so current flows whenever there is a potential difference, right? Between 2 points, if there is some potential what actually we study in Ohm's law, right? So in Ohm's law, whenever there is a potential difference between 2 points, and there is like suppose a resistance there, so the current through that circuit will be the difference of potential by the resistance, right? So here also we have tried to do the same thing. Just wait a bit, okay? Just wait a minute. Just wait a minute.
Hello.
Hello, yeah. Sorry for the interruption. Yeah. So what I was trying to tell is that we need to represent the thermal circuit in terms of electrical parameters. So so that we can understand the temperature and temperature rise and all the other aspects properly, right, with ease. So this is the circuit that I was talking about. So here the potential different, like the temperature difference is equivalent to the potential difference. So this point, the temperature of this point is Tj, which we call as the junction temperature, and the temperature of this point is T ambient, like ambient temperature, the temperature of the ambient, right? So as there is a temperature difference and this resistance, this is the thermal resistance, right? So the thermal resistance is the basically the resist like the thermal resistance we can represent, you can think about it as the electrical resist equivalent to the electrical resistance. So this is basically the uh, resistance of the thermal circuit, right? And the current we represent it whatever in electrical circuit as there is current, and in thermal circuit there is this power loss. So whatever power loss is incurred in that circuit, so that basically is that flows through this, and there like that the heat is generated, right? So this is like equivalent to a current source, maybe this is the power loss, and these two are the junction temperature and the ambient temperature, right? And RTAJ is basically the thermal resistance from junction to ambient. So this is the formula, right? So this resistance is basically Tj minus Ta by this P. So this I already mentioned that in datasheet it is specified what is the maximum allowable junction temperature beyond which the device can't sustain. If we go beyond that temperature, the device will get damaged. So the junction temperature should always be lesser than the maximum limit. And this junction to ambient thermal resistance is basically the summation of two resistances. One is junction to case. So if you see the datasheet of any device, the junction to case thermal resistance is specified, and another one is case to ambient. So if you know the maximum junction temperature, like allowable temperature, and you know the ambient temperature, and you also know the power loss, you can calculate RTHJ, right? And if you know this quantity, and from datasheet you can know this quantity, you can calculate this thermal resistance. And this quantity will help you to decide what should be the thermal resistance of your heat sink, right? So while choosing a heat sink, you should ensure that the thermal resistance should be lesser than this, so that the heat sink can properly dissipate the heat and your junction temperature stays within the limit. Am I clear?
Yes, madam, ma'am. Where does this circuit exist? Is it exist or it is just for understanding?
No, this is not a physical circuit. Like this is just a equivalent model for our understanding. So
Okay, madam.
yeah, so this circuit is quite complex. There is not only one simple resistor, there will be some other things also. But for our understanding, we have made this model so that we can choose the heat sink and we can also compute this junction temperature and all these things, right? So this is for our understanding. There is no such circuit actually. Yeah, so there are, lastly, I will just, before going to the
Sorry,
problems, I
just
will,
a question.
yeah.
Based on that RTH value, how to select on a heat sink?
Yeah, so I will suggest you just go to that lecture and see like Umanand sir's lecture. There he has explained how to select a heat sink and what is its importance. And okay, so now actually I need to show you the problems. So if I get time, I will show you, right, at the end of this session. Or otherwise, you can
Okay.
always see the lecture. There he has explained very clearly how to select heatsink from this value. Okay?
Okay.
Okay, yeah. So that's why, like, I will just suggest, like, before attending this session, kindly please just listen to the lecture once, because in this 2 hour, it is not possible to cover every topic very elaborately. So if you just see it once and try to understand this, then this session will be effective. Otherwise, I can't cover everything. Okay. So from next week, please try to just listen to it. So yeah, so lastly, there are different kinds of diodes that are available in the industry. So there are rectifier diodes, then fast recovery diodes, and ultra fast recovery diodes, and lastly Schottky barrier diode. So basically, uh, if you see, as when I was talking about the reverse recovery phenomena, so it takes some time for the charges to be removed, right? This doesn't occur in zero time. Some time is required to remove all the charges from the junction. So that that time is not equal for each kind of diode. So for rectifier diodes, this reverse recovery time is like large. But for fast recovery diodes, from the name only, you can understand that the recovery time is very small. And for ultra fast recovery diode, the time is even smaller. And for Schottky barrier diode, actually the time is like very almost negligible, almost zero time you can say. So these Schottky barrier diode, these are very fast diodes, right? And they are also very efficient diodes. The power loss in these diodes are very small. So you can check the datasheet for this kind of diodes in the lecture series also. The sir has mentioned the he has showed datasheet for different kinds of diodes, for rectifier diode and fast recovery diode and Schottky diode. And you yourself can also check the datasheet to see like to compare the reverse recovery time, right? So you will see that for rectifier diodes it is larger, and for this Schottky diode or fast recovery diode it is smaller, right? And smaller the time, smaller is the reverse recovery loss. Okay, because then the overlap time between the voltage and current becomes smaller, right? So that's why the lesser the recovery time, the lesser will be the reverse recovery loss. Okay.
Yes, madam. Madam, this recovery current or loss is converted to heat, right?
Yeah, whatever loss incurs in a like loss happens in a device, it is always in the form of heat, and that's why the junction temperature rises.
Okay. So it does not conduct electricity.
Sorry, meaning I didn't understand what.
To rephrase, I said that, ma'am, it just convert it into heat. It does not conduct electricity.
No, this is because this is loss, na. Power loss
Okay.
means it will always get converted to heat. So the whatever power like is like diode is not the load. Diode is just a switch, right? It acts as a switch, and it just whenever it turns on, the electrical power it is like drawn like electrical power is delivered to the load. So whatever power you get across the load, that is your effective power. That is your useful power. And the other power which gets lost as the power loss, that is always heat. So that power you can't retrieve, that is lost. So if
Okay,
you
madam.
just so our actually the aim of power electronics is to design a circuit with minimal loss. Like if you can just design a circuit where the loss is very minimal, then obviously your efficiency will be very high, and and that will be a good product, right? That will be a good design. So our aim is to always reduce the loss, because loss is of no use. It just gets converted to heat and it is lost. So now we will go to the problem solving part. Whatever some questions are there that I will solve. So yeah. So you have some assignment, right, for week 1 that you need to do.
Yes, ma'am.
Yeah. So what is the deadline for that?
And 5th of February.
Okay. Okay, so I hope that after this session you will get some help, right? So I will just go to the problems then. So first question is, so there will be some combination of diodes, and you will have to tell that there is one point A and another point B. So for which combination, so the current can flow from point A to point B, right? So the first option is this. So, what do you think? Can current go from point A to point B in this combination?
No, ma'am.
No,
No.
right? No, right? Because here the diodes are connected back to back, right? So for the current to go from point A to point B, it can't first of all can't go through this diode, because here this terminal is cathode and this terminal is anode, and we know that diode can only conduct from anode to cathode, not the other way, right? So the current can't flow through this path because this diode will not allow it. And this diode will also not allow it, right? So this is not possible for this combination of diodes. So let's see the next option. So this is the next combination. So for this combination, is it possible?
Yes, ma'am.
Yes.
Yeah, right. So the current can flow from this path and then through this, right? This is the path. So right like that it can flow. So is
It
it
can take
clear?
part in both the diodes, right? Because
From
both
this,
are in forward direction.
sorry, right. So from this one as well as through this path. Yeah. So both the paths are fine. Yeah. So this is the next one. For this one,
No, ma'am.
no, right? Again, the same problem. So even though this diode can carry current, but here it will get interrupted. And here also it will get interrupted. So it can't flow, the current can't flow from A to B. Next is this one. So here it is very straightforward. It can flow through this path, right? Is it
Yes.
fine? Yeah. So there are two correct options, option B and option D. Okay. So yeah. So we will go to the next question. So first let's read the question. What it is saying is a diode is connected between DC source VDC, this is the DC source, and load resistance RL. So this is the load resistance whose value is 10 ohm. The equivalent circuit is shown in the figure associated with the diode. So this is the diode and this is the equivalent circuit of the diode, as I already mentioned in the earlier slide, that this is the resistance of the diode and this is the threshold voltage. So this is the actually this whole thing is the diode that is shown here. So RD is given 0.85 ohm and the voltage drop is 1.1, VD is 1.1. So we need to calculate the power drop in the diode, right? So what is the power loss in the diode during conduction? Right. So can any of you solve this? Like, can you or just tell me what is the approach to solve it?
First of all, we will write the
We will write the,
given numbers, given values.
yeah, that is okay. So then what we need to do, what we need to find?
Power loss.
Yeah, power loss obviously, but before, like, what is the first step to compute that?
KCL.
KCL or KVL?
The input voltage equal to output voltage minus voltage drop.
Okay, so if we just apply KVL in this loop, so here we have VDC and we have this drop 1.1 volt, right? So can we write like this? I equal to VDC minus VD by RD plus RL. Can we write this? So just like you just don't see the rest of the thing, just tell me. Can you understand why I have written this current through this circuit is VDC minus VD by RD plus RL? So basically this is my source voltage and from that I need to subtract this drop, right? Because its polarity is like this. So this is the positive terminal, this is the negative terminal. So from this 10 volt I need to subtract this voltage. So this will be the effective voltage and what is the resistance? The resistance will be the series combination of RD and RL. So this is the total resistance. So that's how I need to calculate the current. Is it okay? I have just
Fine, madam.
done KVL in this loop. So this is like IRD, then plus VD plus IRL, and then minus VDC. So if you just rearrange it, the current expression comes out to be this. You can check it. You can verify it later also. Okay. So from that we can compute the current. Once we have the current, then as this is a DC current, so the RMS value will also be 0.82 ampere and the average current will also be 0.82 ampere, right? Because this will be a DC current. So the power loss, we already saw that power loss during conduction is this VDI average plus IRMS square into RD, right? So this VD is already there, and I average and IRMS both the values are 0.82 ampere. So the power loss we can compute from this formula. Okay. So is it fine?
Yes, it's clear.
Sorry.
Yeah,
Uh,
it's clear.
it's clear. Okay, okay. Okay, fine. So if we have time, we will just get back to it. If somebody has any confusion, we can get back to it. Okay. So yeah. So let's go to the next problem. So the next problem is calculate the forward voltage drop of the diode for the figure shown in question 2. So the same figure, what we need to calculate is the forward voltage drop. So now don't get confused. This voltage is the cut-in voltage, right? This is a constant voltage. And the forward voltage drop, what is meant by forward voltage drop? Forward voltage drop means the voltage drop across this whole diode. So these two is combination of the whole diode, right? So that's why it is given like this RD and VD. So the voltage drop will be like combination of this VD and the combination of voltage drop across this RD. So this will be the entire voltage, forward voltage drop. Okay. Not only VD. This is the cut-in voltage or threshold voltage.
It will
So the
be 0.7.
sorry.
Will it be 0.7?
Yeah, that's what I was saying. So see, this voltage, whatever we have, they have given this as 1.1 already, right? They have mentioned that this VD is 1.1. So this is this, if I just go back to, uh, so if I go back here, this is this voltage, this threshold, like this is instead of zero point 0.6, they have told that this is 1.1. So this is a constant voltage, but this is not the diode forward voltage drop, because this voltage will always be there. But as the current is, some current is there, there will be also some drop due to that resistance, right? That I mentioned. It's not only the for this voltage, but there will be some drop due to the resistance also. That comes due to this loop. As the current rises, you can see the voltage drop increases, right? You can see. If you suppose take this point, this is your operating point, and if you come down here, so you can see the voltage drop is more than this, right? 0.6 volt. Did you understand what I'm trying to say? As the current rises, this drop also increases. So at this point, the voltage drop is something like this. So they have given this voltage as 1.1, but still we need to find what is the drop due to the resistance, right? Due to the diode resistance RD. So that's what we need to find. So the forward voltage drop will be this VD plus IDRD, right? Because RD is also present here. So we already computed the current as 0.82 and RD was given 0.85. So plus 1.1, right? So the forward voltage drop will be this, not this or not this voltage. Because diode comprises of this resistance and this voltage, the diode equivalent model. Am I clear? Why this is coming out to be like this?
So this is a total forward voltage, right?
Yeah, this is the total forward voltage drop. And this voltage is that voltage that we need to exceed. Suppose this DC voltage, this source voltage, it was 1 volt. Then the diode can't conduct current because that voltage is less than this threshold voltage. The moment is just exceeds this 1.1 volt, then only the diode will turn on, right? So this is 10 volt and this is 1.1 volt. Now the voltage is sufficiently high compared to this threshold voltage. Now the diode is turned on and it conducts current. So that's why the drop will be this voltage. Along with that, the drop across this resistance, because now the diode is conducting current and there is some drop across this resistance as well. Okay, so this will be the total drop. Okay. Okay, so did you understand? Like, is it clear now? Like, why I did this?
Got it, madam.
Okay, so let's go to the next problem. So, which of the following features are often ideal diode? So, this I think you can tell what are the features of an ideal diode. You can try it, no problem. Even if it is wrong, no problem. You can just try to tell. What do you think?
I'm ABD.
APT, madam.
Right. So A, what it says, on resistance is 0. So obviously for ideal diode, on resistance will be 0. And what B says, off resistance is infinity. That is also right. So as off resistance is infinity, that's why it will not carry any current and it can block any amount of voltage. What does C say? It says that during the forward bias condition, infinite current is conducted in both the forward and reverse direction. But that is not true for a diode because diode can only conduct current in the forward direction, that is from anode to cathode, right? And D says that it withstands infinite reverse voltage during the reverse bias condition. That is also correct because ideal diode can withstand infinite voltage in the reverse direction. So A, B, D, these three are correct. Yeah. So you were right. So let's see to the next question. So this is the question. So consider a current through the diode. The current is IT that is flowing through it. If the characteristic of the diode and the current are shown as in the figure, calculate the total conduction loss in the diode. So this is the current waveform that is flowing through the diode. This is the current waveform and this is the time with respect to time. And this is the diode characteristic. So this is the piecewise linear characteristic. As you can see, there is this threshold voltage and thereafter there is a linear slope. So sorry, there is a linear relation between I and V, right? So this is a approximate model. So again, we need to calculate the conduction loss. So the procedure will be same. So first we need to, the current waveform is already given. We need to calculate the average current and the RMS current, right? Because the diode conduction loss comprises of average current also and RMS current also. So first of all, what we will see, so we know that here the threshold voltage is 0.6 volt and the diode resistance is 0.02 ohm. That is already given. So we need to find I average and I RMS. How will we calculate? So first of all, I already said what is the expression for I average. So the expression for I average is something like this. So integration of 0 to Ts IDDT over 1 by Ts. So this is the average current. And if you do the integration, so from 0 to Ts by 2, the current is 10 ampere, constant 10 ampere. And from Ts by 2 to Ts, it is 0, right? So if you do this integration, what you will get is, you will get 0.5 times 10. So this will come out to be 5 ampere. You can verify it, right, by yourself. You can check like whether it is coming out to be 5 ampere. And for the RMS current, this is the expression that I already told that while I was explaining the concepts. So this is the RMS current expression. So if you do the intercept, the same thing from 0 to Ts by 2, the current is 10 ampere. And again in this period, the current is 0. So if you just divide this time frame into two time frames, so one will be from 0 to Ts by 2, another will be from Ts by 2 to Ts. And if you just put the current values 10 and then 0, then you will get this expression. So 10 times root 0.5. So this RMS current is 7.07 ampere. And once we have the average current as well as the RMS current, we can easily find out what will be the power loss. So again, the same formula. It will be VD into I average plus I RMS square into RD. So we just put the values and we get 4 watt power loss. Okay. So these expressions you can verify by yourself. This is very simple integration. Okay.
Ma'am,
Uh, yeah.
ma'am, what will be the value of TS?
So TS value you don't require actually. If you just compute this now. So suppose, okay, if we just see this integration from 0 to Ts by 2, it will be 10 dt, right? Because the current is constant 10. So you can directly put 10, right? 10 into dt. So 10 will come out outside this integration because it is constant. So dt will be what? 0 to Ts by 2, right? So this will come out to be Ts by 2. Did you understand what I said?
Got it, madam.
Yeah,
Then
and
it will
then again,
cancel the TS.
yeah. So the TS will get cancelled and you will only get 0.5 because it will be Ts by 2 and here it is Ts. So you will get half here and into multiplied by 10. So it will come out to be 5 ampere. And in RMS current also the Ts, like you don't need the value of Ts. You will get this expression after the integration and you can just compute this value. So everybody, is it clear?
Clear, madam.
Yeah, so like if there is any confusion, you just try, like after this session, you just try to compute it. You will get it easily. There is no complication in this. You just verify it yourself how this is coming. Okay. And you can see, okay, for yourself. This is not very complicated. So we will go to the next problem. So yeah. So here they have given the electrical equivalent circuit for the thermal calculations. So refer to question 5 to determine the maximum safe ambient temperature for the safe operation of the diode if the junction to ambient thermal resistance is given as 30 degrees Celsius per watt and the allowable junction temperature is 150 degrees Celsius. So it is given that the maximum allowable junction temperature is 150 degrees centigrade and they have also given the junction to ambient thermal resistance. So the RTH junction to ambient, this is given as 30 degrees centigrade per watt. What we need to find is the maximum safe ambient temperature for the safe operation of the diode, meaning the diode, we need to find the safe ambient temperature so that the diode temperature doesn't exceed 150 degrees centigrade because this is the safe limit. Beyond this, the diode will get damaged. So how will we calculate this? This is pretty simple. So I have already showed you that the junction to ambient resistance, thermal resistance, we can find from this formula, right? This is junction temperature, this is ambient temperature divided by power loss. So we have already computed the power loss as 4 watt, right? This is the power loss, conduction loss. So we can just put it. We already know so here it is given Tj should be lesser than 150 degree, the maximum temperature. So what is Tj? Tj is P times RTH plus Ta, right? If we just rearrange it. So Tj expression will be, the P will come this side plus Ta. So this should be lesser than 150 degree. We already know P. We already know this. This is given as 30 degree centigrade per watt, and we need to find Ta. So Ta comes out to be 30 degrees Celsius. So Ta should be less than 30 degrees Celsius so that my junction temperature doesn't exceed 150 degree. Is it okay?
Yes, ma'am, solved. Same answer.
Yeah. Okay, fine. Okay, others? Is it okay? Others, can anybody respond whether it is okay?
Yes, ma'am.
Okay. Fine. So we can go to the next question. So again, I think we have got similar problem. Based on the circuit and the diode characteristics in the figure below, calculate the power delivered in watts to the load resistance of 40 ohm. So this is our load resistance, 40 ohm, and this is the diode. And this is another, maybe this is a source resistance or some resistance that is present in our circuit, and this is the diode. And the diode characteristics is already given here. This is again a piecewise linear characteristic. So our resistance will be constant because the relationship between current and voltage is linear. So our resistance will be a constant. But here you see, they have not given the RD straight away. You have to calculate it from this slope, right? They have not given it. They have not, like in the other problem, they gave that the RD value is some 0.85 ohm. Here you need to find it by yourself. So how will we find it? It is very simple. We just need to find the slope, right? So I have just found it like this. So here this threshold voltage is between, like this point is between 0.4 and 0.6. So I have taken it as 0.5. So I know the threshold voltage is 0.5 volt, right? Or the cut-in voltage, whatever. And RD is delta V by delta I. So what is delta V? Delta V is the difference between this point and this point, 0.8 minus 0.5. And delta I is from 0 to this point is at 0.9. So this is 0.9. So it comes out to be 0.333 ohm, right? Till this step, is it clear how I got to this value? This is just like V by I have done delta V by delta I from this relation. Is it okay?
Yes, ma'am.
Okay. So we have already got RD value. So then we can find out what is our current, right? Again, we can apply KVL in the circuit. So VDC minus VD divided by all the resistances. So RS, RD, that is the diode resistance, and the load resistance. So the current comes out to be this 1.09 ampere. So the power delivered to the load means this is our load resistance. So the power delivered to this load will be I square times RL. So this comes out to be 47.69 watt. This again you can verify, you can calculate it by yourself and check whether this value is correct. Okay. So this is the power delivered to the load. Next, what they have asked? They have asked that determine the efficiency in the circuit for the circuit shown in question 7. So the same circuit, we need to find out the efficiency. So earlier, what we found out, what is the power delivered to the load? So we already have the output power, right? The power delivered to the load is actually the output power. And the input power is what? We already have the current value and we know the source voltage is 50 volts. So the power daily input power would be source voltage multiplied by the load, the current. So this is the input power. And efficiency is output power by input power multiplied by 100. So this comes out to be 87.35%, right? This is also very straightforward. Is it clear to everybody how the efficiency is 87.35%? How I calculated it? You just need to find out the input power and you already calculated the output power. So you have these two quantities and then you can find the efficiency, right?
Ma'am, 1.0919 is the current value.
Yeah,
Okay.
yeah, this is the current value that we already calculated. And all these things are in series, right? So the current through the diode, current through this resistance, and current through this resistance, the current flowing through all these components will be same, right? Because they are all in series. So that's why I have just added all these resistances. Okay, so we will go to the next question. So this is also pretty easy. What is the blocking voltage of an ideal switch? So that is infinity, as we already saw that an ideal switch can block infinite amount of voltage. So this is infinity, right? And next,
Right,
I
ma'am.
think we have the last question. What is the unit of the thermal resistance? So thermal resistance unit, we can express it as degree centigrade per watt, or we can also express it as Kelvin per watt, as Kelvin is also the unit for temperature. And another watt is basically what? Watt is power. So power we can express as joule per second, right? You know that energy at unit time is the power, right? So if you just put joule per second instead of watt, the second goes to the numerator, so it comes out to be Kelvin second per joule. So this can also be the unit for thermal resistance. So the correct answer will be all of the above. Is it okay?
Yes, ma'am.
Okay. So I think all the problems here are solved. Like whatever problems I had, so all the problems are solved. So anybody has any question?
Madam, is network analysis knowledge is required for this course?
What? What knowledge?
Madam, network
Network.
analysis.
So are you from electrical branch or like from any other branch?
I'm electronics.
Okay, so but you must be knowing the basic theorems, right? The KVL, KCL, all these things are, I think, basic electrical. So I think you already studied all these things in your first year or something, if I am right.
Okay, ma'am.
So do you know KVL or KCL? I actually don't know like all of your like what you were studying exactly. So uh, do you know KVL, KCL, all these things? KVL, KCL, network theorems. If you don't
Yes, ma'am.
know,
A bit
then
of idea.
yeah, if you don't know, then I will suggest just go through. There are like various lectures are available in NPTEL also. There are various lectures available on network theorem and all these things. You can just study it a bit. Not very complicated stuff, just the basic rules and basic laws of network. So then afterwards, then you will get like it will be advantageous. Otherwise, there will you will get problem to understand all these things, because I will be using this KVL, KCL, all these things frequently. If you don't know these things, then it will be difficult for you to understand, grasp the concepts,
Oh, okay, ma'am.
right? So yeah, so if you just can study a bit, then it will be very helpful for you, because you see, like I have limited time, so I can't explain like all these things very elaborately, right? And yeah, also just also go through the lecture of like this E37 lecture series. You can also just go through before attending the session, so that whenever I solve these questions, you will better understand. Just please, it is a request to all of you. Please go through it once and then you can attend the session, right?
Okay, ma'am.
And I will upload this recorded session, and also the this presentation whatever I was showing today. I will upload all these things, and you will get access to this, so you can always get back to these things whenever you require. Okay.
Thank you, madam.
Okay. Okay,
Madam,
so
can we
any
get this from mail?
sorry.
Madam, can we get this? Can we get this presentation mail, madam?
Actually, I will, there will be one Google Drive folder where I will be uploading all the PPTs. So from there, I will also share the link, so you can access them from there. I will share the link, okay? And this
Thank you, madam.
lecture, this recorded session will also be uploaded in YouTube, so you can access it whenever you want, okay?
Okay, madam.
Okay. So then I will just stop recording, okay? I will stop recording. Okay, so, okay.